Today I want to be talking about something a bit complementary to what we've been hearing about today, where the goal is really to use a lot of the tools that have been developed for machine learning, these kind of high-dimensional optimization techniques or inference techniques, back propagation through complicated models, and GPU acceleration to do something that's not machine learning, but is still related to cosmological hydrodynamics. And so the goal is to create a fully differentiable hydrodynamical simulation, so not doing emulation, not baryon painting, nothing like that. Actually explicitly modeling the evolution of the dark matter, the Euler equations for the gas, as well as sprinkling in some subgrid physics. And the goal is to do this kind of lofty title of a unified chronocosmographic analysis. So doing things on the field level, if possible. I think we heard some great talks already and some great discussion yesterday with this kind of lofty goal of really forward modeling everything all the way down to the pixel level. To give away the ending, I'm not there yet, but this is just kind of a proof of principle of a lot of this, that this framework could actually be useful for exploring these high-dimensional spaces. So, I think a lot of talks already covered this, so I won't spend too much time, but I'm really motivated by this idea that if you can really run a simulation that actually reproduces everything at the pixel level, you actually get the spectra of every galaxy that we observe, the actual XYZ positions, the actual pixelized TSZ or X-ray, you can kind of say you solve physics, right? We can all be out of a job until the next new survey comes along that shows something new, right? This is kind of the fundamental idea of physics, is that we can actually do the simulation. As we kind of, a lot of people mentioned, we don't want to trust black boxes for everything. But as we kind of discussed yesterday, there's a lot of tensions already just within the simulations, right? There's no simulation that can actually match the observations. And in fact, as you go beyond like 2 observables, it seems like already nothing matches, let alone including everything across all wavelengths. So the particular observable that I've played around with, although the techniques will be more general, but just to kind of set the stage a little bit, is Lyman alpha tomography. And there's already been a few talks about Lyman alpha 4, so I won't get into that. But the idea of Lyman alpha tomography is that you can actually use these one-dimensional lines of sight to build 3-dimensional maps of the cosmic web, and of specifically the neutral hydrogen content in the cosmic web. So how does that work? Well, we can imagine if we take a little random simulation here of the neutral hydrogen. You can imagine if we have a grid of background sources that are all some super high signal to noise, we actually can get these flux absorptions, and you can almost see by eye the cosmic web, right? You can just play connecting the dots game of the absorption features to construct this kind of 3-dimensional map. Of course, the real universe is not so nice as to give us a perfectly spaced grid of super luminous quasars, and in the end we have to deal with using Lyman break galaxies and all these systematics that pop up. And so we want to use a more nuanced model than just taking a pen to the screen here to connect the dots. And the particular model that I like using is trying to use differentiable simulations. And the idea is to really build a pipeline that goes from our initial density field, so the initial conditions of the universe, the initial Gaussian fluctuations, and associated parameters that we might care about. Run a physical simulation to get some simulated outputs. And I'll be talking both about doing this at the pixel level data as well as summary statistic data. We already saw in the last talk some kind of discussion of doing this at the summary statistic level. And then mapping these to, or having those simulated outputs and comparing them to data in some kind of cost or likelihood function. And if we have this all differentiable, we can make a well-informed update of that initial density field or the initial parameters depending on, or the initial parameters depending on how we set this up. Or you could go beyond simple optimization and do full sampling. So in the context of Lyman alpha forest, the kind of framework is that we have our initial conditions. We used a fast particle mesh solver to get our final density and velocity field. We map that to real space with a hydro model, which will be kind of the core of this talk. We can do redshift space distortion, pick out lines of sight. And because we will see that all these steps can be differentiated, you can actually back propagate through to do this reconstruction. So for the modeling gas physics, there's a lot of choices that you have. So kind of one of the main things people in the field have been doing so far is some kind of analytical approximation or bias model. In the case of Lyman alpha forest, a popular one is the Fluctuant-Peterson approximation. You could generalize this to various non-local or environmental dependent quantities. Something I worked on in the past is using generative machine learning models to map from the dark matter field to the full hydro field outputs. So if people are interested, you can talk to me more about that later. But what I'm really excited about is actually trying to do the explicit hydrodynamical modeling, which will be the later on in this talk. So kind of iterating here again, we're going from initial conditions, final density field, hydrodynamical quantities, likelihood calculation at the actual pixel level. And I also played around with including galaxies as an additional tracer for this. And because this is all differentiable, we can use quasi or semi-Newtonian methods like LBFGS to optimize for the initial field. And so people might have already seen various versions of this, this animation showing the reconstruction. So at the top, we have our true initial density field and mock late-time density field. We generate a mock that emulates the upcoming prime focus spectrograph galaxy evolution survey. And within, order 100 samples, or if you're smart, you could probably do it in a lot less samples, you get a really good reconstruction of the cosmic web. And so the main application of this was to generate cosmic web to cross-correlate with galaxy samples for looking at environment-galaxy relations. So this is holding kind of the parameters fixed, which I guess is what people are probably mostly interested in. And so this type of survey was actually done with the Clamato survey, which KG, Lee, and I led at various times. It has roughly 320, or exactly 320, background sources, of which are both quasars and Lyman break galaxies, where we can observe the Lyman alpha forest. And we applied these techniques to make three-dimensional cosmic web reconstructions. So identifying the highest redshift known filaments and voids and protoclusters. And there's a lot of analysis ongoing with this map that people can feel free to talk to me about later. But of course, we did this whole initial condition reconstruction, so we actually have the initial Gaussian fluctuations that we believe best match the data. And so we can kind of go back a step and say, well, what happens if we feed this into a full hydrosim? And so Chris Boyle in Germany has been playing around with this. And we had actually, just I think about a month ago, maybe 2 months ago, had this paper out on the Cosmos TNG. So this is a suite of simulations that kind of, that has the full TNG galaxy formation model, the repo code for the gas. And so it's basically a suite of simulations that are constrained to match this little patch of the universe. And even though we kind of used a really rough hydro model in our field level inference framework, we found that actually when we ran the hydrosim, it matches quite well at the qualitative level. But we kind of know that FGPA is breaking down when we go into centers of massive clusters, where there's this really complex hydrodynamical physics. And so what we're kind of interested in is, well, this all seems a bit backwards. Can we just run the hydrosim and iterate on the hydrosim outputs to do the same kind of reconstruction? And I guess the answer to that is not quite yet, but I'm working on it to try and make this actual hydrosim differentiable itself, to be the full forward model. And I don't actually know very much about hydrosims. So I like playing the buzzword salad here. But I'm working with Zari Lukic at LBL, who knows a lot about hydrosims. So hopefully by the end, I'll learn along the way. So to kind of give a little toy example to start out with, we can imagine we have just solving the hydrodynamics themselves. So no gravity, constant medium, just 3 little explosions. I found as I played more and more with hydrosims and subgrid physics, it's really fun to make things blow up. But anyway, so we're solving this on a grid. And so basically, I implemented the solving of the Euler equations using a standard kind of numerical routine for solving them. Just implementing it in JAX, throwing in some tricks to still keep the solutions exact at the level of the numerical method, but to allow backwards differentiability. So to actually allow you to back propagate through, do the chain rule through the steps, and actually get the solution. So we can make similar kind of cute videos of this late time pressure field and try to optimize to solve the initial conditions that correspond to this kind of weird bubbly explosion. And you can find another solution that happens to match quite well. This is just doing gradient descent, so nothing too fancy. And it looks quite different. It's very unlikely just to have 3 little isolated explosions. And depending on what exactly you're interested in at the end, you can always do some more advanced optimization method or sampling method. I worked a lot on these kind of optimization and then variations around the optimized solution methods back in my PhD. And so we can try to apply those to these cases as well. But we're interested in making a full cosmological hydrosim, so let's plug in gravity. So here's an example of plugging in a particle mesh routine, jointly solving, again, the Euler equations with the particle mesh evolution, and keeping it all differentiable, because all these is just a sum of linear operators and Fourier operators. You can differentiate each component, so the autodiff routines and JAX make this quite easy. And because it's all in JAX, it's all on GPU and ends up running really quickly. I was very surprised. It takes a while to compile. But once you compile, you can vary the initial conditions, vary the parameters, and I think this sim takes roughly like a minute, or maybe even less than a minute on one GPU. Still toy box, but we can now try to do the full field level inference. So you can see I like a certain type of animation here, because we're going to take this as fake data and try to reconstruct the initial conditions that give rise to this kind of configuration. So this is kind of modeled after some kind of noisy X-ray TSC type observation. So a kind of an indirect measurement of some function of the density and temperature. And in this case, we actually find a pretty converged solution after just 20 or so iterations, where we can actually reconstruct the initial conditions that give rise to this with some kind of explicit likelihood framework. So each iteration here is one hydrosim. I think this was a smaller box. These ran in literally like 5 seconds or something like that on a single GPU. So of course, the dream here is to try to do, as I described earlier, do full field level inference, marginalizing overall galaxy formation models down to redshift 0. I'm motivated a lot by the Lyman alpha forest, so we got redshift 2. Things are easier at redshift 2 versus redshift 0. But the dream is to do this all the way down to redshift 0, marginalizing everything possible, any observable you throw in. But of course, it's good to publish papers before retirement. So I figure it's, we could downscope a little bit and look at summary statistics space. If you look at summary statistics, the dimensionality of the problem you can reduce quite a bit, because you can just average over various realizations of the initial phases. You don't have to optimize them jointly. But you still have a really large dimensional parameter space, right? These, like, as I was mentioning before in one of the questions, Gizmo has 40 or so astrophysical parameters. As you start looking at extended lambda CDM parameters, if you talk to the phenomenologists or the string theorists, the sky's the limit in terms of number of parameters you might want to add in. And so, I guess I'm somewhat skeptical, that as you go to these really trying to understand jointly astrophysics and cosmology, that you can do this in a way that doesn't include the derivative information, doesn't use the derivatives to explore this really high dimensional space. And going back to this kind of poll here about how we're not even sure that the hydrodynamics that we have describe the underlying physics, right? As we've seen already in the talk, simulations and observations don't meet. And I got really excited here for a second, or maybe really worried, because I misread refine, this most popular one, as redefine subgrid physics, which I thought I might have been scooped in this whole concept. But I think what's really kind of powerful about these kind of explicit solving of the physics is you can really introduce super expressive subgrid physics models. If you're kind of in the ML space, you can imagine, have the subgrid physics be a neural network. You can train the neural network parameters on running the actual simulations and comparing to observations. So you can actually train the neural network to reproduce the actual observed things in the real life, which seems like a pretty cool application. And then you can then have priors on these subgrid physics based on small-scale simulations. You can imagine running jointly small-scale simulations, large simulations at the same time, including both physics at both scales. So to kind of give a more simple example of subgrid physics, just to kind of show that it is possible, because you might think these kind of stochastic processes are difficult to backpropagate through, but fortunately, this kind of stochastic backpropagation comes up a lot in industry when you're looking at machine learning models, reinforcement learning, self-driving cars. You want to make sure you make a left or a right, not some weird superposition of left and rights if you're in a Waymo taxi or something like that. So there's some tricks that I don't think I have time to go into, but to basically treat the stochasticity as an input to your model rather than output, and then map this to discrete quantities. I applied this to halo occupation distributions to populate galaxies into dark matter halos, so discrete galaxies. People can ask me about that later. And then we can actually do the full subgrid physics model. So Again, I like showing things blowing up, so here I just turned the subgrid physics up to 11 just to make a cool video. But again, you can back propagate through this. You can take derivatives of all these output fields with respect to the initial conditions, with respect to the underlying parameters. And so here's an example of the earlier simulation, but now keeping track of the star field, the stellar population. So I populate the stars, I keep track of them going forward on a particle mesh grid. And so you can vary, of course, the subgrid physics. We're going to go to submary-statistic space, so you can look at the gas power spectra. You can take explicit derivatives of these. So you could take finite differences, but it turns out if you actually use the automatic differentiation, you do this much faster, and you don't have to run additional simulations. So quite powerful. And so just to give a little toy example here, I generated one fake volume, added in some noise, some covariance, and you can run an HMC on both the cosmological parameters and the subgrid physics parameters. So both, this is omega matter, sigma 8, that critical density scale for whether or not you form stars, as well as the energy injection scale for the stars. And you can jointly solve for all of these. And what was really cool is this worked better than I would have thought. It actually, the HMC sampling was super efficient and was able to really explore this parameter space, which is quite cool. And so fewer simulations than I even thought I would have to run. And so, of course, the goal is, not just one observable, fold in every observable you have, astrophysical, cosmological, and run a big sim, and then jointly fit for all of these things. And so with that, I'll just leave up my summary slide and leave a few minutes for questions. Thanks.
Yes. No, yeah.
Thanks. Are you using diffracts for the ODEs?
I am not using diffracts currently. I have seen the package, and I think it probably will be what I end up using eventually. Okay. I'm not entirely sure exactly how it deals with these kind of complex numerical routines for.
So that was going to be my question. I was wondering if you're concerned about the sensitivity of your solutions as a function of your solver, or like the stiffness of your ODEs.
Yeah. So these things I don't think are really actually. I don't think these things can be technically classified as stiff ODEs. But like in terms of the numerics of them, this is well explored because people have run these hydro sims for quite a while. So I think the worry about the stiffness of ODEs goes into like how you define these time steps and how you change these time steps. But in the end, at least in the cases I've looked at so far, the time steps for your solver don't change drastically as a function of these parameters. So you could maybe get away with just doing a hybrid approach. But yeah, I am, though, curious about implementing the diffracts approach.
Yeah, I've used it a bunch. I'd love to chat about it.
Yeah,
but also, I just had another quick question. So with the backprop, how expensive is it? Like, do you need to adjoint?
So right now, yeah, I did mention possibly adjointing. I think people have looked at the adjoint method for the Euler equations from computational fluid dynamics to optimize wing design and stuff like that. So that is something that's been kind of well studied. I wasn't sure exactly how well I could use the subgrid physics with the adjoint method as you're going back through, if you actually want, because these things might be hard to write adjoint operators for, but that might just be lack of my creativity.
Good qualitative agreement.
Yeah, no, it's a really specific statement, right?
Yeah. When I read that in a paper, I usually read bad quantitative agreement.
Yeah. Yeah, well, it's hard, to make something super quantitative because of the small volume, right? And also the poor quality of data in this region. So it's really hard to say, what type of statistic you can actually observe here that you can actually really then go and make a quantitative comparison to. So for example, we did find that the galaxy overdensity field, which was not used to make the actual initial condition field, actually matched well the observed galaxy density field. But it's one of these things, I'm not going to claim that I can predict exactly where a galaxy is down to the spectra resolution for the redshift determination, right? So yeah, I think Chris was smarter and has a couple other more quantitative plots in the paper that we can look at later.
Hey, This seems really useful. I'd love to chat sometime. Um, h- how do you deal with memory? Like, what's the biggest box you can run, and can you
Yeah.
parallelize over multiple GPUs?
Yeah, so I've not yet currently made it parallelized over GPUs. I think that the actual real limitation for parallelization over GPUs is the FFT operators. And I know I've been chatting with Francois Lanous and some of his students about how to make that. He seems like he has a solution, so I'm excited to take his solution and apply it here. You know, like the actual solving the Euler equations is kind of trivially parallelizable across GPUs because you can just keep track of what's flowing in and out of each box. In terms of the actual memory application, I was pretty surprised by how good it seemed to be about memory. I think JAX has a lot of tricks up its sleeves. So the only thing I was really doing manually was kind of deciding where to checkpoint various kind of compiled bits of code. And so like, yeah, there's a small difference between what I can differentiate and what I can just do single forward models of, but that difference is only like a factor of 2 or something like that. So.
Okay, thanks, Ben. Our next speaker is Aizhan.
Okay, can you hear me okay? Okay, can you hear me okay now? Is this a little better? Louder? Better? Okay, perfect. Okay, so then let's start. Hi everyone, my name is Aizhan Akhmetzhanova, and today I will be talking about this project on detecting model misspecification in cosmology with normalizing flows, or what we call multi-scale normalizing flows. And this is the work that's been done in collaboration with Carol Cuesta-Lazaro and Sid Mishra Sharma. Okay. Perfect. So the main motivation for this project is thinking about how to best connect cosmological observations and cosmological simulations and how to bridge the gap between the two, especially given the fact that different cosmological simulations implement or use different implementations of astrophysical processes, and the effects of these different implementations are going to vary both on the physical field that we're looking at and also based on the physical scale in question. So while they might agree on the larger scales, there's probably going to be a lot more differences as we go to smaller and smaller scales. So when it comes to connecting cosmological simulations and observations, some of the questions that we might want to answer are, for example, how can we use cosmological simulations in order to detect anomalies in the observed data sets? And what are some of the tools that we could use in order to check for the goodness of fit of the observed data? So for instance, we might want to answer questions like, is our data out of distributions with respect to the simulations that are used in the analysis? And also, is the observed data described accurately by the simulations, or are we dealing with something like model misspecification? And then broadly speaking, another set of questions is how can we choose an appropriate representations of the data from the simulations? So some of the questions that might inform our choices are how informative these representations are, do they aid detection of model misspecification, and also what type of representations could help to interpret the ways in which a given model is misspecified. And in terms of some of the approaches to anomaly detection and model misspecification, in the literature, there are broadly 4 different classes of methods that we can separate these approaches into. But the one that we'll be using in this project is a density-based method. So in general, density-based methods model explicitly the distribution of the data, P of x. And then when detecting out-of-distribution examples, these examples are detected by looking whether a sample lies in the region of low probability of the data. However, when it comes to using density-based methods, some caution is required because sometimes in the literature there have been examples where out-of-distribution samples have been assigned higher probability. So usually density-based methods are best used in combination with some of the other methods. So when it comes to the density-based methods, Bayesian evidence is essentially the tool that we'll be using in order to detect model misspecification. And Bayesian evidence is the probability of the data under a given model. And it's described by this. Sorry. Oh, I forget. We don't have the pointer. But it is described by this integral. And one thing that we can see is that this integral is going to be quite challenging to estimate numerically, because it requires an integration of this product of the likelihood and the prior over the entire parameter space under the model M. And over the years, there have been multiple estimation techniques that have been proposed to efficiently evaluate this integral. Some of them are listed here, but the ones that we'll be using in this project are normalizing flows. So in the context of cosmological simulations, what exactly do we mean by the model and the data? So when it comes to the model, this is the hydrodynamical simulation that is used in the analysis, such as, for example, simpler or illustrious TNG. And then the observed data vector could be either like a traditional summary statistic, like power spectrum, or perhaps a neural summary statistic that's derived from the data. Or it can be the uncompressed data itself. And then the parameters are the cosmological and the astrophysical parameters of the simulations. So for example, here I'm plotting the power spectra of the gas fields from the illustrious TNG simulation on the left. And then on the right is a histogram of the evidence of the different samples that I'm plotting over here. So if we're looking at an example of a data point that is in distribution, that could be a power spectrum of gas from another suite of the illustrious TNG simulations. And we can take a look at how the probability of that data point kind of like relates to the overall probability of the distribution. And then for an example of an out-of-distribution data, this could be, for example, a power spectrum of gas from the Astrid simulations or from the Simba simulations. And we can compare the evidence of these data points to the evidence of the data points from the illustrious TNG simulations. So once again, as I mentioned, we're using normalizing flows in order to estimate the evidence. So broadly speaking, normalizing flows learn the target distribution by transforming a simple distribution, such as, for example, a Gaussian, into a complex distribution through a series of invertible transformation functions. And one useful property of normalizing flows is that they can be conditioned on other variables in order to learn conditional distributions. So in this case, we'll be conditioning our distributions on the smoothing scale that's applied to the data products for the simulation. So the framework that we're working with here is essentially trying to estimate the Bayesian evidence as a function of smoothing scale. And we'll be applying it to two-dimensional maps, and specifically to neural summary statistics of two-dimensional maps. So first, we randomly sample different smoothing scales and then apply this Gaussian smoothing process to the maps. And then we pass these smoothed maps, as well as the smoothing scale as an additional channel to a CNN, in order to extract neural summary statistics from the data. And these neural summary statistics are extracted such that they maximize the probability of the true parameters that correspond to these maps, given a summary statistic. And then once we have the summary statistics, we're going to use normalizing flows that take in the neural summary statistics and the smoothing scales for which the statistic was computed, and then estimate the probability of the summary statistics conditioned on the smoothing scale. So now the question is, can these probabilities or can these evidences be used to detect if an observation is out of distribution? So since the CAMELS simulations are still more of a kind of like a model and not so much connected to like observations that we might get from DESI or some other surveys, we'll be using different simulation suites as either a model or an observation. And specifically, we're applying them to the total density matter maps. So we're training our normalizing flows and the CNN that extracts the summary statistics on the illustrious TNG dataset. And during the training process, we're sampling the smoothing scale logarithmically from the So the largest smoothing scales are for the smoothing wave vector k of 2h over megaparsec, and then the smallest ones are for k being equal to 45h over megaparsec. And so here what I'm showing you is what the different maps look like for different levels of smoothing, and also how much cosmological information they contain about the parameters omega matter and sigma 8. And we can see that as we go to more and more resolved maps, the summary statistics that we extract from these maps contain more and more information about these parameters. So now we're going to move on to the evidence of the summary statistics. So once again, we're using the illustrious TNG simulations as our models. And then for observations, we could use a simulation like an asteroid or SIMBA. So this is a plot that shows the distribution of the log of the evidence of the summary statistic for these 3 different simulation suits. And what we can see is that for this level of smoothing, the summary statistics, or the distribution of the summary statistics, of the evidences of the summary statistics mostly overlaps, and there are no significant differences. As we go to a slightly higher resolution, as our smoothing scale becomes slightly smaller, we see that we start noticing a slight shift in the asteroid and SIMBA distributions with respect to the illustrious TNG distribution, but they still seem to mostly overlap. However, as we go to smaller and smaller smoothing scales, we start to see that while illustrious and asteroid are mostly showing the same values for the evidences of the summary statistics, the evidences of the summary statistics of the SIMBA seem to be kind of like consistently lower, or at the lower end of the evidence distribution. And we can see it even better if we compute the average percentile of the asteroid and SIMBA, of the summary statistics from the asteroid and SIMBA with respect to the illustrious TNG. So just one thing to note here is that the variance that I'm showing is approximate, because in the cosmic variance dataset of the CAMELS simulation, some of the maps come from the same simulation boxes. But the main point here is that we see that as we go to higher resolutions or smaller smoothing scales, it becomes easier to detect that one of the simulations, such as SIMBA, is out of distribution from the base model of the illustrious TNG. And then we can also take a look at the principal component analysis of the neural summary statistics to try to understand what exactly they encode that allows them to kind of like separate these distributions. And so as I'm flipping through different smoothing scales, we see that most of the variations happen in the principal components 1 and 2. And if we plot the variation of the principal components of 1 and 2 with the parameter S8, one thing that we can note is that the principal component 1 seems to vary quite clearly as we vary the value of the S8 parameter. So it looks like these neural summary statistics that we got during our training process encode information about the S8 parameter that allows them to detect that one of the simulations, namely SIMBA, is out of distribution. So just to quickly summarize the talk, first we developed a machine learning framework that uses normalizing flows in order to estimate the Bayesian evidence at the level of different summary statistics. So I showed the results for the neural summary statistics, but the same can be done with traditional summary statistics like power spectra or bispectra. We show this application for the total matter density fields from the CAMELS simulations, but it can be extended to other fields, such as, for example, gas density fields or gas temperature. We also showed how it can be applied to probe at which scales are most affected by the differences in the subgrid physics models. And we can compare it across different levels of data summarization. Again, power spectra, bispectra, neural summary statistics, to see which ones are going to aid the most when it comes to detecting model misspecification. And then as some of the next steps, it would be interesting to apply this framework to evaluate the evidence of the fields directly, so skipping the data summarization step, and also to extend this framework to model more realistic observation scenarios. And so this is my final slide. Thank you so much for listening to the talk, and if you have any questions, I would be happy to answer them.
questions? Yes.
Thanks. Yeah, super interesting. So I was just wondering if you could use this framework to like help train models that are more robust and that hopefully can, yeah, produce unbiased predictions when even when tested in like maybe auto distribution models that perhaps I don't know, knowing that you can maybe depending on a scale. Anyway, so do you have any thoughts on this?
Yeah, no, I think it's definitely one thing that could be interesting to experiment with. So, for example, perhaps we could try to figure out if there exists some sort of summary statistic that takes information from like different types of scales. But still that the distribution of the summary statistics is kind of like uniform across different simulation suits. And in principle, this could be an example of a more robust summary statistic. I'm not really sure how exactly we would do it in practice, but I think it's definitely something that could be considered.
No more question? Oh, Matt.
Hi.
So in the distributions that you were showing at a given smoothing scale, there were some Simba simulations that did have a, not the best evidence, but like a somewhat close evidence to illustrious TNG.
Yeah.
I wonder is that like a particular region of parameter space of the Simba parameter space, which is illustrious TNG-like?
Yeah. So all of these were shown for examples of the maps from the cosmoclarian set, so they all share the same cosmological parameters. What is different for these maps are different initial sets. But it does seem like some of these simulations do have evidences that are kind of like closer to perhaps the mean evidence of the, for example, illustrious TNG suit. So I think in this case, this method would probably work best for if we have the type of data that is not just a single observation, but perhaps like multiple observations that all correspond to the same data. So maybe instead of like having, I don't know, like a single map of the sky, we would separate our sky into different subvolumes and then just in general look at kind of like what on average that evidence looks like. Yeah.
Yes.
Yeah, very nice work. So my experience working with the total matter field is actually one of the, maybe the only thing where you can train in one and usually work in the other. But according to this is that the still Simba is kind of an outlier.
Yeah, so in this case, it seems like Simba is an outlier. However, we tried to do this, for example, for the power spectra, for the matter density fields. And if you look at those, then regardless of the smoothing scale used, it seems like the distribution is pretty much the same across different simulation suits. So I think it really does depend on the type of like summary statistic or the level of the data summarization that you're using.
No more question? Okay, we're right on time.
Oh, there was
There's
one.
one.
I don't know if
Lucas.
Oh, do you mean the length of the summary statistics vector, or?
That, or the amount of descriptive power and the depth of CNN?
Yeah, one of the things that we noticed was that actually this CNN that we were using, ResNet 10, which is kind of like a more lightweight version of the standard CNN, of the standard ResNet network, was actually giving us better results when it comes to kind of like compressing the maps down to the most informative features in the summary statistic. And I think perhaps it has to do with the complexity of the maps. So, yeah.
Okay, so thanks, Aizhan. Okay, so for the last talk before lunch, we have Nesar. So
Thank you. So this is yet another talk on subgrid model calibration for cosmology simulations, but it's not CAMELS. So I'm Nesar Ramachandra. I'm a computational scientist at Argonne. And this project was a collaborative effort between Argonne, Los Alamos, Virginia Tech. So let me see. So we work with the simulation code called HACC, hardware hybrid accelerated cosmology code. So this HACC code is really meant for scaling into really large supercomputers. So we try to run on millions of ranks. We go to gigaparsec scales. We run trillions of particles. So extreme scale simulations. And because we run these large simulations, these are very attractive for big surveys like DOE Rubin or NASA Spherex. So these are the places where we create different maps, extragalactic catalogs, and all these simulation products are consistently being used. So the newer versions of HACC now couples the traditional n-body solver with we have a smooth particle hydrodynamics code, and then there are also subgrid models, just like a lot of other codes out there now. One thing you can see here, now that we have all these models, one thing that we can do now is we can look at different fields and particles. So you can look at this dark matter field here, star particles, and Aizhan particles. Sorry, it's not very clear. And finally, there is gas, so all for a same core. And then different effects here are on the y-axis. So we are successively adding different effects. So initially, there is multi-species gravity only. And then there is some adiabatic effects that are added. Then a bunch of subgrid models for cooling, Aizhan cooling, star formation, galactic outflows, and Aizhans. Even though it's not very clear what difference these things make, you can still see these in summary statistics. And maybe if you really zoom in, you can see them very clearly. But all these subgrid parameters, just like all the talks we listen to, these have to be calibrated into observations. But there are a lot of complexities apart from all the machine learning frameworks that you can use. Even in the model scales, and even in the subgrid models, you often see that these subgrid physics models are very stochastic. They're very local models and extremely resolution dependent. So you have to be very careful about these subgrid model calibrations. And we are dealing with a lot of heuristic techniques. And then there are systematics in observations that you have to take care of. There are biases that we have to be very careful about including them. Coming to emulators, with running HACC simulations, we've been creating a lot of different emulators since 2008, starting with things like Coyote Universe, which was meant for dark matter part spectra. And since then, we have both extended these emulators into larger and larger K range. We've gone to sub-percent levels in terms of accuracies. We've extended it to different summary statistics like halo mass functions, concentration mass relationships. So there is a whole bunch of ensemble of emulators out there. But more recently, we've also started doing more survey-specific tools, like emulating 3x2 point functions. We're emulating SEDs. There are like modified gravity models and early dark energy models, these like beyond omega CDM models that we are emulating. One of the posters by Niyantri Krishnan today is going to be about the early dark energy model, so please go check. Apart from that, we are also going into higher dimensions, so using neural networks, diffusion models to create things like galaxy images, neural networks, et cetera. The plot you see here is a constraint on this modified gravity model called Hu-Saviki. This was based on LSST-like data. You can see both Fisher ellipses and MCMC posteriors. And the plot at the bottom is I think it's a 6-dimensional emulation or a mapping going from initial conditions to some high redshift, some low redshift field. And this was done using diffusion transformers. So all these new methods are really useful But I would still claim that when it comes to dealing with very small number of training points, and if your error requirements are extremely high, like you really want robust error estimates, then Gaussian process is still probably the king. You still get really good results, and you can deal with low number of training points. Okay, so that's about the emulators. So I'm going to go to some of the subgrid models. Subgrid models in Hack, we have a whole list of them. So right now, we are only concerned about 2 of the subgrid models. So one is about the galactic outflow, or the wind model. And this is very similar to the SN1 and SN2 in the CAMELS data set. So there is a wind velocity and available energy. So that's 2 of the parameters. And for AGN feedback, we have 3 parameters. So there's a thermal model that is parameterized by the seed mass of the black holes. And then for the kinetic feedback model, we have 2 parameters, one for the velocity of the feedback events, and other is the efficiency of the accretion rate of the black holes. So that's the epsilon. And then in addition to that, we have subgrid models for chemical enrichment, star formation, metal line cooling. But for this particular talk and this our current effort, we have restricted it to just these 5 parameters here. So going forward, once we are very happy with the calibrations here, we'll probably go to the next ones. Okay, the calibration framework is essentially very similar to all these emulation-based inference methods. So starting with some of our HPC systems, we run an ensemble of hydrodynamic simulations. So with the 5 parameters I showed earlier, we select a range of those parameters. We run a bunch of simulations. And from each simulation, we extract summary statistics. So these could be things like galaxy stellar mass functions, cluster gas fractions, and all this. And on the other side, from the observations, we can look at different sources. So we can look at photometry, we can look at X-ray telescopes, and we can get equivalent multiple measurements of cosmology. And when it comes to the inference, we can compare them both. So essentially, the statistics and the machine learning framework comes in between your simulations and observations. And once we are successful with our calibrations, we are happier with our subgrid models. The eventual goal is to create a really large capstone hydrodynamic simulation, and that has to be run on one of the exascale systems. One thing I should tell is, so currently all these ensembles that are run, we have not really used the exascale systems. But this one, the capstone simulation, indeed does use one of the exascale systems. Okay, so the training points that we are using, like I mentioned before, we have 5 subgrid parameters. And again, we go with the traditional approach. We start with an experimental design that involves a Latin hypercube. We have decided to go with 64 simulations with a side length of 128 megaparsec over H. Sorry about that length. And from each of those 64 simulations, we have extracted multiple summary statistics. So there's galaxy stellar mass functions that you can see there. That's for all the 64 simulations. And I think I'm coloring by one of the velocity parameters. There's cluster gas fractions. There's cluster gas density. There's black hole to stellar mass relationship. There's a big list of summary statistics that we are extracting. Not all of them are emulated, and amongst the ones that are emulated, not all of them are used for calibrations. So we make certain choice about what kind of statistics we want to use, depending on the systematics in the observations, our mass resolutions, our box length, etc. One of the things that I wanted to note is this cluster gas density. So cluster gas density is the density profile of the clusters. And so it's a radial profile. One thing that happens when you deal with small simulations like 128 megaparsec cube boxes is you do not get a lot of clusters over 10 raised to 14.5 solar masses. So we have almost no clusters at that scale. And that's a concern. Because when you look at the cluster gas fractions, what you really see is At low radius, you see a dip in the profile because of that low number of clusters. And so what we did is for one of the simulations, we ran an equivalent of a 256 box. So just a larger box, everything else is the same. And then we just computed what's the discrepancy, like an addition term that we can use, just to make up for that factor because of the low sampling that happens on the cluster scale. So that is added here. So what I'm showing here is sort of a corrected profile. And that's important because that's important in the next stage when I talk about like phase 2 of the simulation, which I'll get to in a few slides. And then comes the observational data sets. So for mapping all this, we go across like a whole bunch of different observations. From Sloan, we have multi-band photometry, which is used for the cluster gas fractions. For galaxy stellar mass functions, we use gamma high-resolution spectroscopy data. We use X-ray data from Chandra and XXL for cluster gas densities and galaxy fractions. And we use HSC's weak lensing measurements, mass measurements for galaxy fractions. For the cluster gas fractions. And you can see all these blue dots here. Those are these observational data sets. And you can see the coverage of our emulated summary statistics and the observational targets. All right, so we have the bunch of simulations. We run the emulators, the Gaussian process emulators. The process is the usual, like you do your PCA, go to your weights basis, do a mapping from your hydro parameters to the weights, and do a reconstruction using PCA again. And then you end up with a surrogate model that's really fast, and you can do a lot of other things other than just using them in inference. One of the nice things is you can start looking at the sensitivities. So what we are showing here is the variation of different summary statistics with the 5 parameters. So the 5 parameters, the first 2 wind parameters, the thermal AGN parameter, and the kinetic AGN feedback parameters. One thing to note is for like galaxy stellar mass function, you see a decent variation with respect to the first 3 parameters. But when it comes to the kinetic AGN feedback parameters, you don't see a lot of variation. But on the other hand, if you look at cluster gas densities, you do see a lot of variation here. Again, this is sort of important for the other things that we are doing in the future. Apart from this, we can also do Fisher analysis. A lot of, and let me show the MCMCs next, which is why we are doing this. One of the things I wanted to inspire upon is why we are doing this joint calibration instead of going with like one summary statistic. These parameters that are used in the subgrid physics often manifest in a very complicated way when you look at the summary statistic. And it's often not very obvious, right? So and because of that, we have to run these. If you look at the difference between running just one forward model, like in a single likelihood, versus if you successively add different summary statistic in your joint likelihood, you can see the differences in how tighter the constraints get. But in addition to that, you also see sometimes there are multiple modes, and some of those modes can go away when you add when you increase your components in your joint likelihood. This here is shown for the 2 parameters, but we essentially see this everywhere across all the parameters. So even in things like kinetic parameters here, galaxy stellar mass function itself does not constrain much, like you saw earlier. But then addition of cluster gas fraction and cluster gas density really starts constraining your parameter as well. With this, I go to the emulator application. So we did run a full 5-parameter MCMC, and we do notice that so the 2 contours I'm showing here are the are the joint likelihoods with galaxy stellar mass function and gas fraction, and the other one is all 3 components. So we do get pretty good consistent posteriors. But one thing to note is when I take like the best fits from my MCMC and I see how they match with the observations, this is when you see that the galaxy stellar mass function and the cluster gas fraction match really well. But when you look at cluster gas density, because of the issues that I mentioned earlier, because of like small count in the clusters, you do see some kind of discrepancy here. And this is concerning, right? Even though we have like consistent posteriors, we have quite a lot of bias here. And so that just points us to having a bigger simulation. And that puts us in a fix because hydrodynamic simulations are really expensive. So if you want to go with like double the box size and maintain the resolution limit, that's like 8 to 10 times as expensive. So we really did not want to run a full suite of emulation, and we stuck to a limited budget of like something like 16 simulations. And now we only want to get the cluster gas density right because that's where the problem arises, right? So, and the cluster gas density primarily dependent on the kinetic feedback parameters in the AGN. So that's the two parameters that we are varying, and we repeat this process. So we start a new experimental design. We go with 16 parameters just in 2 dimensions, build new emulators, run a new MCMC. This time I'm using cluster gas density as my forward model. And then there is another statistic of the cluster gas densities for like these low entropy clusters, which is also some data that you can get from X-ray targets. And once you do that, you get the new set of constrained optimizing parameters. Now, of course, this is not an automated way of doing it. This is like a multi-stage approach, but we are doing the active learning by hand. But essentially, this sort of gives us a good idea about the amount of complications that go in when you have to constrain subgrid parameters. So with that, I'm going to conclude. The next steps, we do have a lot of plans on constraining subgrid parameters along with cosmological parameters and things like simulation-based inference. Some of the things that you saw, like when we deal with two different simulation sizes, you often have to deal with like multi-fidelity Gaussian processes and all these unified approaches that are really interesting. And one thing I wanted to say was all these subgrid parameters that were obtained from the MCMCs, these were meant for running a really large simulation, and we have in fact finished a very large simulation box run on one of the exascale supercomputers. And Nick Frontieri, who is going to talk all about it on Thursday, so I will not give any more details. With that, if you have any questions, let me know.
Questions? Yes.
Great, thank you for your talk. I was curious why you stopped at density for your gas.
For cluster gas
Yeah.
densities? Why not?
I mean, because it's only part of the thermodynamic information.
Yes.
And in fact, there's a lot of degeneracies if you don't include, say, temperature or pressure, which would help break the degeneracies with various subgrid parameters. I mean, we've showed this on the CGM scale.
Yeah,
that's the same on.
I saw that. Yeah, we can definitely include that. We are pretty much going at this systematically. We have looked at things like cluster gas electron density profiles, but yeah, we've not really done temperature or pressure profiles yet.
I mean, pressure profiles exist from Planck already, and the same subset of X-ray clusters where you have the gas density. So
yeah, we can definitely do that.
Empirically, the biggest concern was when we discussed these massive feedback simulations. The biggest tracer of the issues with clusters was the density profile because it blows out all the gas. Once you match those as we did, then temperature and pressure profiles seem to match pretty well. We just haven't emulated them in the calibration process. Right, but you still have like there is degeneracies, as you're saying.
Yeah.
Absolutely.
Yeah, and those should go away when you include.
Quite specific question. You have the efficiency for the black hole accretion and all that.
Yeah.
Do you assume, first of all, what do you mean by the efficiency? Is it normalized to the maximum possible Eddington limit accretion rate, or do you mean something else by that? And also, if so, do you account for different possibilities like sane or meta accretion because they it may give you different accretion efficiencies, even for the same system, but at different epochs.
Yeah, I'm going to redirect that question to Nick again because he's been running the subgrid models.
It's equivalent to the TNG equivalent of like
Yeah.
the same type of prescription.
Okay.
This is all TNG type of
Okay.
simulations.
Yeah.
Yeah.
Lines, I see your velocity best fit parameters are like 8,000 kilometers per second.
Mm-hmm.
That's kind of outrageous for standard stellar feedback model parameter values. So what are they really denoting?
Yeah, so
We start to worry that we might be violating the regular
yeah,
physics.
so you see that 8,000 sort of value in when you do this 5-parameter fitting, and that was part of our concern that it seems way too high, and once we start doing the 2-parameter model, that's when you see that it's actually reduced quite a bit.
But that is that what just one parameter summarizing both the stellar feedback and black hole feedback all at once?
No.
Independent of the mass scales that you're considering. In reality, galaxies have different efficiencies,
Sure.
low mass galaxies, high mass galaxies, because different physics works in different mass scales.
Yes.
So you're not capturing that. You're just putting everything into just one parameter.
No.
Is that correct?
No. So it's the same galactic. You still should do it as the same like TNG wind-like model velocity, which is not what you're showing.
Okay.
Which is a few hundred kilometers per second.
Okay.
1,000. And then this he's saying is roughly about 1,000 to 2,000 kilometers per second for the kinetic feedback large events. So roughly like 1,000 kilometers per second, which I don't think is crazy for a kinetic AGN injection event.
For stellar, it's a bit crazy, I think.
Yeah,
The regular galactic wind is like a few hundred
Right, so it's not
kilometers
galactic
per
winds
second.
in AGN kinetic.
But low mass end, you're using the same velocities,
No.
right? No.
That's what I'm saying. It's the galactic wind is the TNG wind model, which is not this velocity.
Oh,
And that
different.
means scales- yeah, that's what
Okay.
I'm saying. They're different.
Okay.
Yeah.
Okay.
In you are building an emulator, are you using any trick like these perfect simulations or a carpool to suppress cosmic variance?
Right now, not a lot, no. So we did run a lot of different tests on like an ensemble. Like this is just one of our final products. We did run for cosmic variance. We are not doing anything right now.
So for point parameter space, you only have one simulation.
Right now, yes.
And all of them have the same seed, the same random seed?
Yes.
Okay.
Yeah. But we have run different experiments on variant seeds and having realizations.
Okay, last question.
So thanks. Yeah, maybe a bit of a generic question. So I guess any subgrid model with a given number of free parameters, like here you have 5 parameters, then you're trying to find the best fit to a number of observations. So I guess the model is not guaranteed to be flexible enough to fit everything, and especially if we add more and more observational constraints, then it becomes harder and harder.
Yes.
And so I guess, very generic question and issue for everybody. I was wondering if you have any thoughts on how to move forward. I guess building like more flexible models and can accommodate more observations, or sometimes there might be even observational constraints that might be incompatible with each other because of like different observational issues.
I think that sort of teams up a lot of the discussion yesterday and of this conference, right? Like my personal opinion is that we do have to figure out some of the models really well, because I think increasing the number of parameters in the subgrid models in order to do our calibrations, it brings about a lot of different issues. Like I think yes, we have to go with more and more observations. It does seem to constrain things a lot more and break the degeneracies. But going with more number of subgrid models before we figure out some of these primary subgrid models is not going to be very useful. But we should not discuss more about this. Yeah.
Okay, thanks, Nesar.